Welcome, everyone, to our talk today on the future of the web and immersive computing. My name is Brandon Jones, and I'm a developer on the Chrome team that's been driving forward immersive web standards. So we feel like 2018 will mark the true kickoff point for what we've been calling the immersive web. The technologies involved have all begun to stabilize enough that we can begin exposing them to the web platform with confidence. And while the APIs that we'll be discussing today are still in development, if you start learning how to use them now, they'll be shipping in stable browsers by the time you're comfortable with them. So what do we mean when we say the immersive web? Well, it's a collection of new and upcoming tech that prepares the web for the full spectrum of immersive computing, which includes virtual reality and augmented reality. More generally, we think of the immersive web as anything that gives the web a sense of depth, volume, scale, or place. Here's how we think about these technologies in general. Virtual reality, or VR, can take you anywhere, while augmented reality, or AR, can bring anything to you. We'll be covering both in this talk. First, I'll cover how we're bringing VR to the web today. And then John Pallett will come up and show you our upcoming efforts to do the same thing with AR. So let's start with virtual reality. Chances are you already know about VR headsets like the Daydream View, the HTC Vive, or the Lenovo Mirage Solo that was released just last week and is on display here. They use a combination of head tracking, screens, optics, and controllers to make you feel like you're present in a different place when you use them. Last year at I/O, we presented the WebVR API as a way for web developers to communicate with these devices. WebVR was really well received, but it also had limitations that became apparent as the VR ecosystem grew. Since then, we've been collaborating with content developers, device manufacturers, and other browser vendors to address those limitations. And the result is the new WebXR device API. WebXR replaces WebVR, evolving the concepts that it introduced to meet the needs of a growing immersive computing ecosystem. It'll serve as the foundation for the immersive web, exposing not just VR, but soon AR functionality as well to web developers. But it also goes beyond the headsets to make those immersive worlds accessible to as many people as possible. Of course, we recognize that migrating existing code to a new API is a bit of a pain. But we also think that the benefits will be well worth the short-term inconvenience. The WebXR API was designed by listening to lots of feedback from developers of real-world content just like you, and explicitly addresses many of the issues that they reported. Additionally, the new API provides a platform for AR features and will be more forward compatible with a wider range of devices. It's also cleaner, more consistent, more predictable, and enables browsers to apply more optimizations. So, what do I mean when I say optimizations? I really like this part. The design of the WebXR API has allowed us to better tune the rendering pipeline. We do it by doing things like reducing the amount of texture copies that Chrome makes internally when presenting VR content. As a result, we're seeing that on Android, we can default to using 50% higher resolution render targets than WebVR did without impacting the application's performance. And all of that technobabble means that we're pushing twice as many pixels to the display versus the same content in WebVR. Put simply, your immersive content looks better and runs faster simply by using the new API. So when can you start using it? Well, today. Developers who want to try virtual reality features on the web can do so today in Chrome 67, which is currently in beta. There are two ways to get started. First, the WebXR device API is available as an origin trial today. Origin trials are a way for Chrome to allow developers to deploy features to users that aren't quite finalized yet by embedding a token in your page header. In return, the developers agree to provide feedback on the feature so that we can improve it prior to shipping. Now, if you're not interested in actually deploying content today, but just want to play around with the API, you can also enable it via Chrome's About Flags page to start testing. And if you enable the API through either of these methods, you gain access to a variety of different ways of viewing immersive content. First, WebXR in Chrome 67 gives you access to mobile VR devices on Android, which enables users to slide their phone into a headset like the Daydream View or Cardboard and instantly turn it into a virtual reality headset. Of course, we recognize that there's a wide variety of mobile devices and browsers out there, which is why we're also making Cardboard compatibility available for other browsers like mobile Safari via JavaScript polyfill. As you might expect, there are some limitations to going that route, but it allows developers to guarantee a baseline functionality to all users. Next, Chrome 67 also supports high-end desktop headsets like the HTC Vive or the Oculus Rift on Windows. These represent the highest quality VR experiences available to consumers today and provide an excellent opportunity for progressive enhancement of your immersive apps by adding things like room scale movement and 6-degree of freedom input. And finally, Chrome 67 also supports what we call magic window content. Magic window refers to viewing the scene on a 2D web page that still tracks the device motion. It provides both a hint to the users that there's a larger world to see and a way to consume the content even when a headset isn't handy. So let's take a quick look at how we can use this new API to create a simple virtual reality application on the web. We're going to assume that you already have a webgl scene that you would like to make viewable in virtual reality. First, we need to detect if there's any WebXR devices available, and if so, we need to advertise that functionality to the user. To do this, we'll start by calling the navigator.xr.requestDevice function. The promise that it returns will resolve to an XR device, which may represent a mobile device with VR and AR capabilities, a wired desktop headset, a standalone headset, or some other type of immersive computing device. Next, we check to see if the device supports the mode that we want to use. In this case, because we want VR content to display on a headset, we ask if it supports exclusive access by the page. If it does, we add a button to our page to advertise the XR feature. And when the user clicks on that button, we'll request what's called an XR session. The session is what gives us access to all of the actual capabilities of the VR or AR device. You get a session by calling request session. And you call that on the XR device we retrieved previously, specifying again that we want exclusive access to the display. Then, once we have the session, we need to create two supporting objects, a frame of reference and a WebGL layer. The frame of reference tells us how to position objects in the scene relative to the user. Here we're asking for a stage frame of reference, which attempts to place the scene's origin on the user's floor. That way, it's very trivial to line up your virtual floor with the user's physical one. Next, we create a WebGL layer, which gives us a surface to be rendering our 3D scene into. You can think of this kind of like a canvas element that's visible from within the headset. Then, once our setup is done, we're going to kick off an animation loop by calling request animation frame on the session, which is very similar to the window.request animation frame you're already familiar with. Now, with that, we're almost ready to begin rendering, but first we need to understand a new concept introduced by WebXR, and that's views. The WebXR renderer loop provides your application with a list of views that must be drawn every frame in order for the scene to appear correctly on whatever device you're viewing it on. A view provides all of the values needed to render a single image of the WebGL scene, such as view and projection matrices and frame buffer viewports. Most headsets will require you to draw two views, one for each eye, while a magic window scene will only require one view. And you can imagine in the future we might have more exotic hardware that could require you to draw even more views than that to account for different display configurations. The benefit is that WebXR can use a unified rendering path for a huge variety of different devices and display modes. And here's how that looks in practice. Our request animation frame callback is given an XR presentation frame object, which contains the list of views that we need to render. It also allows us to query the pose of the XR device, which is its position and orientation in space. To display our scene on the headset, we're going to bind the frame buffer provided by the webgl layer that we created previously, and then begin looping through each of the views that's provided by the frame, drawing into the viewport that each of the views describes, using the view and projection matrices that they provide. And when we put it all together, we can now provide an immersive virtual reality experience with the WebGL scene that we had previously that works on mobile, desktop, and standalone VR devices. But of course, your users aren't content to just look. They want to interact with the immersive worlds that you're creating. So we need a form of input. Now, WebXR took to heart a lot of the feedback that we got about the difficulties handling input with the WebVR APIs. And it attempts to address them with a new unified input system that works across all of WebXR's various form factors. The basic idea is this. Anytime you're interacting with a scene, whether by tapping on a magic window, looking at an object and clicking a button on a cardboard-style headset, or using a controller point and click, all of these interactions can be described by a ray, a point of origin and a direction into the scene. By using the rays that WebXR provides, you can trace into your scene, determine what objects the user wants to interact with, and respond appropriately no matter what input method they're using. So let's see how that looks in code. First, the user needs to know what they're pointing at. So we'll visualize whatever input method they have by going through and querying and iterating the list of input sources from the WebXR session. And then for each input source, we'll get its current pose, which describes the direction the input is pointing in, and, if it's applicable, the position and orientation of the controller as well. Then, depending on the type of input source that we're dealing with, we'll render some combination of a controller model, a pointer ray, and a cursor to show where the input is pointing. And here you can see an example of how an app might visualize a tracked controller. It's rendering both a representation of the controller itself and a pointer ray and cursor to help the user better target their input. If we were using a gaze-based system like Cardboard, we'd only render the cursor because it is fairly distracting to have a laser coming out of your forehead. Thank you. Now that the user can see where they're pointing, we need to be able to respond to what they're clicking on in the scene. And to do this, we listen to the select event. This fires on the XR session and tells us which input source fired the event, which we can then use to query its pose at the time the event happened. This gives us the pointer ray. The application can then use the ray to perform a hit test against its internal representation of your scene. And if we detect that that object was selected, we trigger the appropriate behavior, which will depend on the context of your app. And this allows us to provide users with a way to easily point and click and interact with any object in the scene and have that interaction be consistent across all of the various devices that they might be using. WebXR's input system also allows for grabbing and moving objects by listening to the select start and select end events. And crucially, the select event also is considered by the user agent to be a user activation event, which was not the case previously with WebVR, and one of the issues that we heard about from developers most frequently. This means that applications can start media playback with WebXR input just like they would a mouse or touchscreen. So we now have an interactive VR experience that lives on the web, and that is awesome. But not every user has a headset. And even if they did, not every user is using a browser that supports WebXR yet. Now, we want your content to be accessible by 1 billion+ users. And that's why we're expanding the immersive web's reach to 2D screens via Magic Window and to non-WebXR-enabled browsers with our JavaScript polyfill. So first, let's talk about Magic Window. As I mentioned earlier, it's a mode that lets users view immersive content on their phone without a VR headset, tracking the orientation of your device to let you look around. It's like you're holding a little portal to another world in your hand. And with the WebXR Device API, we've put a lot of effort into making the creation of Magic Window experiences as frictionless as possible. Let's rewind just a little bit and look at our XR session creation code from earlier in the presentation. This code indicates that it wants to start displaying content on the headset by specifying it wants exclusive access to the display. But with Magic Window, we want our immersive content to show up as part of the page and not on the headset. To accomplish this, we only need to make a few changes. First, we create a canvas that we want the Magic Window content to display in, which can be attached anywhere you want in the document. And then you need to get an XR presentation context from that canvas. This works just like getting a webgl context out of the canvas. That gets passed to the session request as the output context. This binds the session's rendered output to that canvas. Now, you'll also notice that we've dropped the exclusive argument from the request because the session's output isn't intended for the headset. And honestly, that's it. Like, everything else is the same. The render loop we described earlier now knows to only request a single view. The input system now fires events that correspond to screen taps rather than controller clicks. And everything else just kind of works. Even better, it's easy to use both Magic Window and VR on a single page, so you can let users transition frictionlessly between the two at the touch of a button. Now finally, let's talk about the WebXR polyfill. For browsers that don't support WebXR, the polyfill provides an implementation of the API in one of two ways. First, it offers a JavaScript-only implementation that works on any mobile browser that exposes orientation events, even mobile Safari. Secondly, if a browser implements the older WebVR API, the polyfill can actually emulate WebXR on top of it, taking advantage of the native hardware features that WebVR already exposes. This means that you can instantly make your new WebXR content accessible to a much wider range of users simply by adding one script to your page. And WebXR isn't the only way that we're bringing immersive computing and the web together. With the Chrome 67 beta, you can now launch a VR-optimized version of Chrome straight from Daydream Home. We've put a lot of work into making browsing the traditional web a great experience in VR, but it also really shines as a way to browse immersive web content. The ability to hop from the 2D web to VR content and back at the push of a button makes discovering new VR content online really easy, fluid, and honestly, just a little bit magical. So, as we've shown, Chrome is fully embracing the immersive web, both through VR browsing and through VR web apps. But what about augmented reality? Well, to talk about that, let me hand it over to John Pallett.
Thanks, Brandon. My name is John Pallett. I'm a product manager on the Chrome team, and I'm going to talk to you about augmented reality. For those of you who don't know what augmented reality is, if you've tried out AR stickers in photos or used Pokemon Go, or if you've used Snapchat filters, you have already used augmented reality. Unlike VR, where you're completely immersed in a virtual world, the idea with augmented reality is that it overlays information into the real world. So if you've used any of these experiences, then you've already tried AR. Now, what's great about augmented reality is that there's over 100 million phones and tablets already available that support augmented reality, and that number is growing rapidly. And generally speaking, those devices already have web browsers. That means that augmented reality can be a real convenience for users. They can walk around, experience augmented reality, and they don't need to install a new app each time. It's great for developers too, because if you want somebody to try out your AR experience, you can throw up a QR code or a URL, and then the user can jump right into it, do the experience, and then leave. The web is going to make augmented reality super convenient and accessible for everyone. So that's great. The web is a great fit for AR. How many of you are web developers in the audience? Can I see a hand? Yeah. How many of you have a website? I hope that's about the same number, given that you're web developers. So the flip side of this is, OK, great, web helps AR, but does AR help you, a web developer? So there are actually a lot of ways that augmented reality can help you enhance your site. And I'm not going to talk about it anymore. What I'm going to do instead is show you what I mean. And I'm going to give you a preview of what's coming soon to Chrome Canary. Can we switch over to the device, please? Okay, in this demo, good, it's working. In this demo, it's actually somewhat of a true story. In this demo, my daughter and I are researching in Mexico City the Templo Mayor, and it was the center of Aztec worship and built in the 14th century. And the temple was built for both the god of rain and agriculture and the god of war. And so what we're learning about here is the use of chacmol statues, which are used to make offerings to Tlaloc, the god of rain. And so we're learning about that here, and if we go down on this page, what I can do is jump into augmented reality mode to learn more. And so it's learning about the scene, and what I can do is I can place a chacmol statue right here into the stage in front of me. Now, this really lets me get in and get a sense of the real-world sense of scale. In reality, it's 45 inches long and 36 inches high, and we can see it's actually life-size. It's a life-size representation of a human being. You notice on the website and through some of the other websites that we saw that a lot of them have this 90-degree head orientation. And so if I go into here, what we can learn is that that 90-degree head orientation is actually fairly common, but so is the pose. Because this chacmol, you could see, is reclining on its back with its knees and its arms bent. And that's traditionally, in art forms of this time, a symbol of humility, of submissiveness, of being a prisoner. In this case, it's probably humility to the deity. There's a bowl for making the offerings here. And what's interesting is I can see little bits on the arms and legs representing iconography. Let's take a look at that. So this is interesting. So if you have a chacmol and it's celebrating the rain god, it's normal to see frogs and marine life and symbols like that. So let's take a look around and see if we can find any. I don't actually see a whole lot here. There's something interesting on the cheek. But there's not a ton of that kind of iconography here. So it's interesting to wonder, okay, well, how did they know that this chacmol statue was actually associated with Tlaloc? Well, if we go down to the feet, what we learn is that the feet are red and they have a hint of blue in the sandals. And this coloring actually helped researchers connect. Here, let's see if we can get a better view of the blue. You see it's tucked in right there in the corner. So this actually gave researchers the clue that they needed to connect this particular chacmol, which was the first full-color chacmol that was ever discovered with the original paint, back to other pieces of artwork from the same time period, which talked about the rain god. This chacmol model was 3D scanned by SciArc in 2016 in collaboration with the Templo Mayor Museum. The data is available for anyone. You can download it, use it for educational purposes through the Open Heritage Project on Google Arts and Culture. Now, I want to stress this is not available to all Chrome users today. These APIs for this are in development, but what we want to do now is show you how to use them and get your feedback before they become firmed up. Let's switch back to the slides, please. So what you just saw was the ability to take an existing two-dimensional web page and add an augmented reality experience to it. This is straight up the biggest opportunity for web developers with AR, because it means you can take amazing new experiences and add them to your existing website. And there are a lot of different websites today that can get some value for users by allowing you to place virtual objects in the real world. Let me give you a few examples. One of them is shopping. In this case, we're looking at a furniture website, and it would let me place furniture elements into the real world. My family recently bought a new couch, and we ended up cutting and measuring pieces of paper and placing them on the floor to make sure that the couch would fit. I could tell you from personal experience, this would have been a lot easier. As you saw, another great use case is education, where anybody can drop an object into the real world and look at it. This is great for statues. There's a painting at the Louvre that's double-sided, where you can get a much better sense of what's going on. And as we explored that statue, I hope you saw you can get a lot more information and learn a lot more than you can from just a static image. There are a lot of other opportunities as well, such as avatars, games, AR stickers, and more. In a mobile context, there are tools that we can provide right now to you that will make your web pages more delightful and increase their value to users. This is coming quickly, and it will make the mobile device a handheld window into a new reality. So let's talk about how these APIs are taking shape. They're being developed in the W3C Immersive Web Community Group. It's a cooperative effort with a number of companies, including Google, Mozilla, Microsoft, Samsung, Oculus, as well as other companies and web developers. This is where the WebXR specification is being developed, which includes the VR APIs that Brandon spoke about earlier. But there are also some more bleeding-edge APIs that are being worked on within that community group. Some of them are more baked than others. I'm going to spend most of my time talking about the top two, AR sessions and hit tests, which were the two building blocks of the Shockmole demo that I showed you earlier. You'll notice that hit tests are in the experimentation stage, where the other ones are still being proposed. So what that means is they're more than just discussion, but not quite ready for origin trials. And practically speaking, that the demo that I showed you earlier will work in Chrome Canary within the next week or two. Basically, by the time you get home and you watch this again on YouTube, it should be ready for you to try. When you do that, you're going to want to enable the two flags that we show here, the WebXR Device API flag and the WebXR Hit Test flag. So this is great. This means an early version of augmented reality is coming quickly to Canary. So let me show you how you can actually get started using it. Well, good news, because it's based on the WebXR API, a lot of the code that Brandon already covered around VR applies here as well. What that means, things like capturing device pose, device orientation, and position are exactly the same. And so switching from VR code to AR code, it's mostly doing the same thing. So what I'm largely going to focus on here are the differences. The first thing to point out is that AR sessions are still in the proposal stage. We're still having conversations about the best way to do this. What that means is that when you enable these flags in Canary, you're going to have a temporary way of enabling AR mode. And you may recognize pieces of this code because it's similar to what Brandon showed you earlier when creating a magic window session, when that is not an exclusive session. Well, if you enable the AR flags in Canary, we're going to make the assumption that you always want AR. And what that means is that the camera will be rendered behind our geometry and kept in sync with the device pose. In the future, the community group is still discussing how we're going to extend and allow the declaration of an AR session. It's likely that the properties will be part of request session. It's not finalized yet. So just for now, if you're trying this out and you enable the flags in Canary, know that it will go into AR mode automatically as long as you create Magic Window, and it will keep everything synchronized. One other difference from Brandon's example is the frame of reference. Where in VR, you were using stage, which aligned with the floor. Here, you're going to use eye level. And what that means is that the first recorded position and forward orientation of the device becomes the origin. And every other motion is relative after that. The y-axis is always aligned with gravity, so it's perpendicular to the ground plane. But when you use eye level, it starts wherever the phone is, and then everything else becomes relative after that. And it's important to use that when you're trying out AR mode. So now let's talk about the real building block that allowed the demo to happen, which is the hit test API. It's the foundation of the demo that I just showed you, and what it lets you do is cast a ray into the real world and detect real-world geometry and shapes. So if I were standing here, I could cast a ray, and it would tell me that there was a podium there. It would also tell me there's a backside to the podium and a floor. I don't think it goes all the way to the mantle of the Earth at this point. So to demonstrate how we use the hit test API, think about a reticle. If you haven't heard that term before, what a reticle is, it's an indicator that's drawn on a real-world surface. In our example, this was useful because it allowed the user to figure out where they wanted to place the object in the AR scene. Now, what you're doing when you're drawing a reticle is you're continually doing hit tests into the real world and then using the results to place geometry into the scene so that it appears as if it's on top of a real-world detected object. Now, before I show you any code for this, what I want to say is that we are using 3.js, which is a helper library for 3D graphics on the web. It takes care of a lot of the heavy lifting for 3D geometry management and rendering, and some of the code we're going to talk through is specific to 3.js. If you're interested in learning more, you can visit 3js.org. In this case, what we're going to do is we're going to create a mesh, or some geometry, for the reticle. So that circle that you saw on this slide and the Shockmole-sized box before is actually 3D geometry with texture on it. And it doesn't really matter what geometry you use, so I'm not going to go into the details. And neither does the permission when you create it in the scene. All you have to do is create it, add it to the scene, and what we're going to do is update the position on the fly as we get back our hit test results. Everything we do next is going to be part of the request animation frame loop. And this is basically the same as you saw in VR, and is brokered through the WebXR session. So you request a frame, and then you execute on it, and at the end you request another frame and continue doing things that way. Now, a key part of this example is that we're going to be using our 3.js camera for a couple of things. One is obviously for rendering, and what we're going to do is update it with the view and the projection matrix from the XR device pose. This ensures that the camera is aligned with our augmented reality device pose and is using the correct frame of reference. So important for rendering, but we're going to use it for something else as well. In every frame, we want something to place our reticle on. And as I mentioned earlier, the hit test API will allow you to cast array into the real world and get back intersection points with real world objects. But to do that, we kind of need array in the right coordinate system with the right frame of reference. And the great news is that 3.js gives us a way of creating that, letting us take our camera and generate array from it. What we'll do is we'll use 0, 0, which in the coordinate system here is the center of the screen. If you're going to try to cast array based upon a user tap, you'd use anywhere from -1 to +1. But in this case, we'll stick with 0, 0. That's where our array, center of the screen, is going to go. And then we'll pass that in to the camera and get back array. The next thing we're going to do is use our XR session to request a hit test. This is the new API that is available when you turn on the flag, and this is the one that is going to be coming to Canary in a couple of weeks. When we do the hit test, what it's accepting is both the origin and the direction of the array. So you can see above, we extract that from the array that we generated, and it also accepts the overall frame of reference as a parameter. And what we get back is a list of hits. And they're ordered in terms of how close they are to the camera. So the first hit is the nearest one to the camera, and then they're sorted by distance. But we want our reticle to be on the first thing that we saw, not the last thing, so we're going to take that one. And then what we'll do is we'll use the matrix that we generate from the hit result and then apply that to the reticle model. And that's it. At this point, the reticle is now positioning itself in real-world objects within the request animation frame as you move the device around. Now let's talk about how to place objects in AR. There's one slight difference here that we probably want to consider. When we get back a hit test, what we get back is both the position of the hit, but also the normal of the surface that the ray detected. And we didn't dissect that before because we wanted our reticle to appear as if it was on the surface. But if you're placing an object in space, you probably want to specify your own orientation, especially which way is up, and instead of using the normal on the real-world object that was detected. The good news is with 3.js, this is fairly straightforward. And what we'll do is use the decompose method, which will extract the position, the quaternion, and the scale from the 4x4 method. Now that these have been extracted, you can change the orientation of the object to be whatever you want, either by generating a new 4x4 matrix or by setting rotation on the object directly. The key point here is that there are situations where you'll want to decompose the hit test result and use pieces of it. In this case for object placement, but in other cases where you want to generate an understanding of the real world within your code, you can get a lot of useful information from these hit test results. The last thing that I want to cover is an API which is only in discussion at this point. This is not coming in Canary, but it's really important to augmented reality, and so I want to cover it so that you have an introduction to it right now. This is a core concept to augmented reality, which is why we're going to cover it here. The concept is anchors. Anchors allow the augmented reality system to keep virtual positions and orientations, poses, always correct and up to date as the system learns over time. So what do I mean by that? What I mean by that is that if you think about the augmented reality system, it doesn't have perfect information. Everything it's getting is from the camera and from sensors and so forth, but it's learning about the real world. As I move the camera around and as it gets more information, it's improving its understanding of the world. But what that means is that sometimes it was wrong previously and it learns that later on. So that's where anchors come in. Anchors allow the underlying augmented reality system to keep track of poses that you care about and improve their accuracy later. So to give you an example, suppose that the augmented reality system thought my camera was here when I did the hit test, but later it realized the camera was over here. What it could do with that knowledge, if I anchored the object, was adjust its location after the fact when it realized its mistake. Anchors are also useful in a lot of other places. For example, when real-world objects start to move. As you can imagine, the whole concept of anchors is both very useful but it's also one that's deep enough that it's continuing to go in conversation. So it's not ready for you to try right now. How to do this as a web API properly is a topic of conversation. But even with a hit test API, which is all that you saw, the session was being created and then a hit test API, there's a lot of opportunities for you to start looking at how you might enhance your existing web pages. The hit test I showed you can let you do pretty much everything on this screen now: shopping, education, and more. And really, all I showed you was placing one virtual object into the real world. There's a lot of information you can get from a hit test and a lot of things that you can do with that. And frankly, we're all really excited to see what you come up with and ideas you have for ways that you can make your website better. But this brings me to another point. There are over 100 million devices that do AR today, but not everyone does. So what do you do in that case? Well, I mentioned earlier that there's a lot of code similarity between AR and VR. This is really important if what you want to do is create a new AR experience, but then also make it available in VR for users that aren't using a device that supports AR. For example, a desktop that doesn't have a camera, and they're not going to pick it up and move it around the room. In that case, what you might want to do is have the exact same code driving a VR experience on desktop with a magic window. In that case, you'd have to adjust your user experience and your user interface. So instead of walking around with your desktop, you would give them controls to be able to zoom in and zoom out. But if you think about the Chuckmole demo, you could still explore the statue and learn a lot from it. That ability to do progressive fallback is super important on the web, and we're really excited that WebXR allows us to do that without having to rewrite the same experience twice. So, just to recap, Brandon and I have talked about the WebXR device API, both for VR sessions, which are available for Origin trials today, and AR sessions, which are still in discussion. We also previewed some augmented reality APIs, which you can try in Chrome Canary. Actually, one augmented reality API, which you can try in Chrome Canary in a couple of weeks. As I mentioned, the conversation is still ongoing for sessions and anchors. And if you're interested in tracking that conversation, this is the slide you should take a photo of. Because we would like you to learn about this. What we really want is your feedback. We'd like you to try it out and let us know what you think. If you try the API and you want to suggest changes, this is where you should go. If you want to track how things are progressing, this is where you should go. Please do visit the community and file issues if you have questions, or file issues if you find things that you think should be different. Overall, though, we're very excited to see what you create with this, both for VR as well as for augmented reality.
Mike?
Oh, one.
And one last thing that we wanted to mention is that a lot of the 3D media that you saw on the slides today was taken from Poly, which is an excellent repository for 3D assets created by tools like Blocks and Tilt Brush. They're all available under the Creative Commons license, hence the credits, and you can check it out at poly.google.com.
If you want to get started with development, there's some links on this screen where you can see how the community group is progressing, as well as seeing code samples. The App Spot link there is the demonstration that I showed you earlier. It will not work today. If you pull out your phone and go to Chrome Canary and turn it on, it will not work. Give us a couple of weeks. But please do try it out and let us know what you think.
Yeah. And if you have more questions for us, we'll be available at the web sandbox, which is over on that end. And thank you so much for joining us today, and please enjoy the rest of Google I/O.